Hello there and welcome back to this video series on control systems. We have seen a very general definition of TF as the ratio of Laplace transform of output to that of input with all zero initial conditions, and we have also seen that transfer function of a linear time invariant system is characterized by its zeros and poles. This video is like an introduction to what we are going to do in later videos. We'll briefly see how a TF is derived from a bird's eye view, how a TF is derived for any general system. The content here may be slightly vague, but as I said, this particular video is given only as an introduction to what we are going to do later in subsequent videos. So just go through it and note down what you think is important. We are going to consider several types of systems, types in the sense electrical systems with RLC circuits, or mechanical systems with spring mass damper, and then fluid systems, maybe hydraulic or pneumatic, and then electromechanical systems, motors and generators, thermal systems involving heat storage and flow, and so on. Some real-life systems may involve combinations of all these elements. For example, we may have electro-hydraulic mechanical system that consists of elements of all these types. So we try to see how we derive a transfer function of any given system. It's a very general method. For each of the systems considered, we have what are called physical principles. For example, it's a spring mass damper system. We have Newton's three laws. Okay, law 1, Newton's law 1, 2, 3. Similarly, for electric systems, we have Kirchhoff's laws, voltage law and current law, and other conditions. For example, you have for fluid systems, you have laws of hydrostatics and hydrodynamics. Laws of thermodynamics, the three laws of thermodynamics, the laws of motor generator action. That is, for example, if you have a electrical system, you use Kirchhoff's laws. You have a mechanical system, you use Newton's laws. Here you use laws of statics and dynamics. Here you use electrical laws, electromagnetic laws. Here you use thermodynamic laws, and so on. So given any system, you use these physical principles. Using these physical principles, you write equations that describe behavior of each element in the system. Once you have the equations for each element in the system, then you take Laplace transform, you eliminate unwanted variables, and you derive transfer function. Thus, given any system that we want to analyze, the procedure is the same. For each element in the system, you write the fundamental principles, either Newton's laws or thermodynamics, laws of thermodynamics or electromagnetics or whatever. For each element, we invoke fundamental principles and write an equation, and then impose system level conditions to indicate the way the elements are connected together. And then identify what we consider as input and what is considered as output, because ultimately that is ratio of Laplace transform of output to that of input is the transfer function. And then eliminate the unwanted variables. You get the TF. In summary, we may say that TF of any physical LTI system may be derived by using fundamental physical principles on each element. And once this is done, either using simple algebra or block diagram reduction or signal flow graphs, which we are going to see later, we eliminate unwanted variables and derive the transfer function. That's all we have for now. Have a great day.